So I made a few changes to the schedule. Well, basically, I've put the submission to start today. So I've released it today, so that you have a bit more time. So instead of just 4 weeks, now you will get 5 weeks to work on it. So I've put the deadline a bit further ahead also, but I've put the start even further ahead. So instead of starting the submission here, I think it was, so I've put it forward 2 weeks, and I've put the deadline also forward 1 week. That's just so that I have enough time to make sure that I get to correct all of them and give you comments on it. A little bit because I was starting to look at my total deadlines here, and we were getting the third submission of the CAD and everything in the same space there. So if I was going to be able to give enough comments on everything, it was better to put it a bit forward. So not everything can be done in the submission yet. There are some of the questions that we have to know something from part 3 and part 4 before we can answer them. But the first couple of questions are possible to answer already. So that's why I've just released it, so that you can start working on it if you want to. Or if you want to save it until the 27th and get just a couple of hours to work on it, then that's fine by me, but that's worse for you. So I would recommend that you start looking at it and answer what you can answer now, and save the rest for a bit later when we've gotten to it. So we'll that's the schedule there, and it's in the submissions folder on the side there. Yeah? No, it's just that I get we had the deadlines for both the CAD and the submission were originally set really close on each other. Submission 3 later on. You're only on submission 1 in CAD yet. So you're going to have submission 2, and then you're going to also have submission 3. But the problem was that submission 3, there's quite a lot to correct on it, because it's a larger submission compared to the first 2. So I have a lot to correct there, and I also have a lot to correct on this one. So putting those two pretty close to each other, that wasn't really all that smart if you were going to get constructive comments that you can use when you are reading for your exams. So that's why I want to push this one a bit forward, just so that we get comments on it. So it's 6 questions. So the first 5 questions are on the first page. The second is on the 6th one is on the last page. You have to write it in a processing software, so Microsoft Word, Apple Pages, Google Docs, whatever. It doesn't really matter, just so that you've written it digitally. Save it as a PDF and upload it on Fronto. And all 6 questions have to be answered in order for it to be approved. And like the first one, the first couple of ones is a bit about subsea production systems, which is part 2 of the compendium. So those are possible to answer already. The 5th one is specifically about ROVs, but it should be possible to answer that one in 1 or 2 weeks. And then the last one does have some calculations in it, and we are going to get into that a bit later on. What it is that we're going to calculate a template that's going to be lower down to the sea bottom. So we're going to calculate the hydrodynamic forces that's going to be working on it as we are lowering it. And what I've used is, just so that you will all get your own individual assignment, I've put in that the length, width, and mass of the template that you're going to do your calculations on all depend on the 3 last digits of your student number, so that everyone will get different numbers in there. And also, last note is that all of these submissions will be run through a database called eForus, and that's one that checks for plagiarism, so that it checks that you haven't exactly copied text from a textbook or from one of your fellow students' submissions. Because as soon as something is uploaded into that database, it will automatically be checked against everything else. So just so you know, that is something that's going to happen, so I would recommend everyone to answer with your own words. Don't just copy-paste text from other places. Write it with your own words and describe it with your own words. That's the correct way of doing this. So that was the submission there. You have 5 weeks or so on it. Either it's 5 weeks minus a couple of days, or it's 5 weeks plus a couple of days. I didn't do the maths on it yesterday. I also figured out what the host abbreviation was when we were looking at the Åsgard stuff. So it's basically hinge over subsea templates. So it's got to do with the fact that they have these, let's see if it's on the, I was on the next one. It's got to do with these parts that they are hinging, that are hinge, which they are putting up when they are lowering it, and then they are lowering them when they get down. So that's why it's called a hinge over subsea template. So because I remember there was something, there was an abbreviation linked to this, but I couldn't really remember what the words were. So, so we got that one. I think it will be easier to just fast forward to where we were by doing this. So the last thing we looked at last lecture was this map. So we were looking at the considerable lengths that we have here. And then this Langeled pipeline, which goes all the way to Great Britain, which is over 1,100 kilometers long. So it's pretty hefty, putting all of that down. And just imagine that everything is put together by 12-meter pipeline parts that have been welded together all the way for 1,100 kilometers. That's pretty far, and quite a lot of pipes. Here's a map of the seabed profile for the pipeline route from Aukra and out to Ormen Lange. So in here is the shore. So here we have Nyhamna, which is the land. And then you have Bjørnsundet, which is very close to land. It's fairly deep, so it's easy for ships to pass and everything. It's another problem. You see it's all the way down to 200, about, and even deeper. And you see it's really, really jagged here. So it's pretty difficult to place your pipeline here. You have to do a lot of digging, and you have to build up underneath the pipeline, because if you have these mountaintops and valleys and you're putting your pipeline, you can dig down from the top here and sort of create it a bit easier to put the pipeline up here. You create a trench from the top down here, put the pipeline inside it, but you might not be able to get the pipeline going all the way down here. So then you have to actually fill in with a lot of gravel and stuff beneath it just to give enough support to the pipeline. Because the pipeline, it can handle being suspended across gaps like this, but the gaps can't be too wide. So that if the length here becomes too long, the suspended length of the pipeline, you have to fill in with gravel beneath it. So a little bit is okay, and that's some of the things that they do when they run surveys along pipelines, when they have ROVs basically just following the pipeline and filming it with their cameras. One of the things they're checking for then is that the ocean currents haven't washed away all of the support material beneath the pipelines, because it can actually do that. And in areas where too much has been washed away, they actually have to come back in and refill so that they get enough support for the pipeline. Yeah.
How is one able to read this map? What's on the
These are the depths. So up here you have sea level. That's the top here is sea level. And as we go along here, you have all of the kilometers. So 120 kilometers out to here. And then you're out by Ormen Lange. And here you have the depth shown. So you have 100 meter depth, 200, 300, 400, and then all the way down to 900 is there. And Ormenlange is around here. So we get all the way from the start. You can see it's gets pretty deep very quick, a couple of 100 meters, but then it goes up again. So we have this sort of top here. So they actually have to somehow manage to get the pipeline across here. And as you can see, this area is really pretty wide. It's several kilometers wide. So you have to sort of get the pipeline up again and then over it. So you can't just, it's not as sharp as it looks here. It's not just a sharp mountain ridge that's up there. It's a pretty large area. So you have to put the pipeline across it. You can't just dig a trench into it. Because if it was really sharp, you could have cut a trench through and get the pipeline in there. Get a nice placement for your pipeline. But here you actually have to go all the way up and then down again instead. So it's a lot of work doing this, a lot of preparation work where they go around with their ROVs before they're putting down the pipeline, just trying to find the very best route of placing it. So they survey the areas, create very detailed maps of the areas just to try to see where can we put the pipeline that will basically cost the least amount of money. It's going to cost a lot of money anyway, but how can we sort of minimize the cost here? And after they were done with this Bjørnsund area, it was a bit easier. You can see it's fairly flat, the rest here. But then you get over to the slide area, where you had that great slide in the last ice age. And there it's very, very steep coming down to Ormenlange. And that is sort of a challenge in itself, because if you're coming from land when you're putting down the pipeline, when you get over here and you get these really sharp slopes, you've got this slope going down here. You're going to put the pipeline down. You got the vessel up on the surface, and the vessel is putting down the pipeline sort of like this. But as the vessel moves along, let's see if I can use another color here. As the vessel moves along over here, the problem is that the pipeline will get a really heavy bend down at the bottom here. So it's actually better to start off at the deeps and pull it up along the ridgeline instead, so go the other way when you're putting there. So I can't quite remember if they went from both directions on this one and met in the middle, or if they just started out here and went all the way in. I'm not quite sure, so I'm not going to say for sure what they did. But it is something that you have to think about when you're putting down your pipeline. It is that you don't want too heavy bends on the pipeline while you're laying it. So just from shore and out to Ormenlange, there is also 720 kilometers of lines going through the water, whether they are pipelines, flow lines that run the production flow, or whether they're injection lines or umbilicals. So all of those together, 2 umbilicals, 2 injection lines, and 2 flow lines, 720 kilometers of lines being put down. So when you think just from land and out to Ormenlange, it was almost as much, 1,100 was the amount that they used from Nyhamna all the way to Easington, I think it is, in Great Britain. So it's they put down almost as much in this shorter distance, which was only 120 kilometers, just because they had to put down so many lines of everything. And here you can see they have to, in the background here, you can see they had to spread them in order to get them up this huge ridge where the landslide was. So this is basically just trying to figure out the best routes of putting them, so then they spread them out just to get each of them into their own best route up there. And then when they were on top on the up top here again, they sort of gathered them back together so that they could run easier surveys on them. It's easier to do a survey if you can sort of keep an eye on all of them while you're moving along them. But right down here, they actually have to split off because it's easier to put them down that way. So this is an illustration just to show a bit how they manage to navigate along the seafloor when they are installing pipelines. So what they've done here is that they have put down these transponders. They send out acoustic signals. So they're basically just creating pinging sounds. And I think each of them have their own frequency, so that the system that's receiving them knows which of, if it was this transponder or if it was that transponder it's listening to, so that it knows which of it is. And then it also calculates the time it takes. So it knows exactly when each transponder is sending its signal. And then it records exactly when it is receiving its signal. And then by calculating the time difference, it can say that, well, I'm a certain distance from this one, which means that I'm somewhere around this circle. But I'm also getting a signal from this one, and that tells me that I have to be around here somewhere. And then if I'm also getting a signal from this one, you can really pinpoint it. So with the two transponders, you can get a fairly precise location. But with the signal from three of them, then you sort of get, then you know exactly where you are. And if you get from even more of them, then you're just in luck, because you have more than you need. You need 3 transponders in order to get a precise location. And this is shown fairly near the shore, where it was this really deep part beyond Sunde. So it's shown a bit how they put out these transponders. And then they used them as they were laying the pipeline here. They used the transponders to tell themselves where exactly are we. So I think actually the flow line is the one going here along this path, and then these are the umbilicals and injection lines, if I'm not quite mistaken here. You can also see these sort of red spots in here. Those are areas where they've put down gravel to build up the pipeline to support it. And you can see here it's really rough terrain they're working in. You have these high tops around here, and you have this deep trench that they're putting the pipeline through. So the whole point is to try to find, basically just like if you're walking a mountain trail, hiking in the mountain, you want to find the trail which is easiest to walk along when you're walking along the mountains. That's what they want to do with the pipeline also, find the easiest path through all of these obstacles. It's just a bit more difficult to do it down on the seafloor. And here we can see the rock installation ship. What it does is it has this sort of riser going down to this sort of dispersal unit. And what it does is basically it just drops rocks down this tube all the way down to the seafloor, and where this dispersal tube is sort of guiding where it's landing, so that they can use it to fill in exactly where they need to fill in all of the gravel and stuff. So this one is sort of a carrier ship. It's filled with gravel, and they're just continually sending a flow of gravel down this pipeline, filling up this area at the bottom. And they used approximately 2.5 million tons. That's quite a lot of rock. And as you can see here, they are letting the pipelines and umbilicals and everything, they are letting them get free spans. So from this point to this point, they are stretched, they are just hanging there. They don't have any support, but they have the support in this flat area and in this flat area. And those are areas like these where they have basically just built up with the rock, so that they can place the pipelines on them. And then when they're doing surveys, what they have to check is that there is still enough support in these areas to keep the pipelines in place. And some areas, like you can see further in here, they've actually covered the pipeline a bit. And that is a way of protecting it, because you see the sort of mountainside here. If they are worried that there might be a slide from that one, that can be quite violent, so it can damage the pipeline. But if the pipeline is already covered with gravel, then the slide is going to go on top of the gravel instead, so it's not going to harm the pipeline much. So that's also one of the things they do with these rock installation ships. They actually call it for rock dumping, so it's a pretty straightforward term. And here we can see a lot of the rock supports they used in Bjørnsundet. In order to get it, you can see all of these blue lines that are crossing it. So there's quite a lot put in here. They also had to dredge a lot of seafloor. Dredging basically means just excavating a lot of the dirt and the sediment that's down there. So 2,000 cubic meters in 2004. That's quite a lot of cubic meters. If you have a regular what's it called? A regular trailer for your car. Just a regular trailer that you can pull with your car. You can usually fill 1.5 cubic meters on those. If you're transporting sand or gravel or something, then you can usually get from between 1 and 2 cubic meters. So usually around 1.5. So that's quite a lot of trailers when they have 2,000 cubic meters. And this is often done with sort of ROVs, but they're not flying through the water. They have wheels or belts so that they are placed on the seafloor, and they are not neutral in water, so they actually have weight in water. They stay there on the seafloor, and then they drive around just like an excavator would on land here. And the principles are a bit different from an excavator on land. An excavator on land will use its shovel and it will just dig and dig, while often on the seafloor you will use water jets. So basically what you're doing is you're creating suction with a water jet in a pipe, and then a different part of the pipe will then be angled down into the sediments, and then the suction created by the water jet through the rest of the pipe will start sucking the sediment through the pipe also. So you basically are just sending it off to the side here and just gathering it in huge piles. And that's mostly the way they do it. So it's sort of a combination of an excavator and a vacuum cleaner, almost. So it's a really cool seeing those. I don't have any good clips of them in action, because usually it's the few clips that I've found of such of dredging done. It's so filled with sediments. It's basically just a fog, so you don't really see much. If you know what you're looking for, you can manage to see it. But if you don't know, it looks just like a fog. So I haven't bothered putting them in. Here you see one of the spiders, as they're called, that they used. So they have these yellow wheels that they're running on. That depends a bit on the sediments on the seafloor. If they can use wheeled ROVs, or if they can use, or if they have to use belts on them. Depends a bit on how much they're going to sink into the sediments. So that also, of course, depends a bit on the weight of the vehicle. So like this one, it does have buoyancy elements on top here. Those yellow ones we can see on the top. They are buoyancy elements to make it lighter in water, but it still has a negative buoyancy, so it won't float. Like an ROV might sometimes be adjusted in such a way with buoyancy that it will actually, if you cut all the power to the thrusters, it's going to slowly just rise to the surface because it's just floating. While this one, it will sink if you release it. So it will sink, but it won't sort of slam down like a rock. It doesn't have all that much weight. So maybe 50 to 100 kilograms is what they try to achieve often with stuff like this. These might actually be a lot heavier in order to get enough traction on the wheels. So they might let them be up towards a ton or something in order to get enough traction on them. A vehicle like this will easily weigh a couple of tons, at least probably 4 to 5 tons also. Yeah?
After the operation, is it the crane that will still leave it up, or the crane will remain in the...
Yeah, it will be lifted up by the crane because it's connected at all times because it has its umbilical and power supply. Goes through the lifting wire all the way up. So all the time while it's working down on the seafloor, it's connected to the vessel. So they pull it up when they're done. And they are pretty expensive, so just leaving it down there would have been a very bad design flaw if they had to leave it. So here's a map where they've tried to show the scope of work for the spiders. So all of these yellow spots in here are places where they had to dredge sediment away in order to create trenches for the pipeline to run through. So they had quite a lot of work with that also. And this is in the landslide area, so the very steep incline here. So you see, even in the steep incline, they actually had to create trenches into it just to get the pipeline at a better angle when they were putting it up. This one was the... here we have an overview of the flows in the system. So here we have the future template C and D, which at the moment of creation for this presentation hadn't been put into place. I'm pretty sure they're there now. I haven't checked it, but I think it was in 2011 or 2012 they put them in place. But up here you have template A and template B, which were the first ones they put down. And here you have the methyl ethylene glycol system, which is the injection system that they're using. And they inject it down here, and then they inject it into the flow. So it's going into the different templates, and it's connected over to these future templates also. But it's actually injecting this methyl ethylene glycol, MEG, into the production flow. Because they had these problems with the low temperatures, that they had negative degrees Celsius in the water here, minus 1.2 or what I think it was. So they insert it into the production flow so that they avoid icing inside the system. It's not directly icing, but it's a fair analogy to call it icing. And here you have pig and slug catchers, as they're called. So they're the ones that will sort of receive pigs when they're sending pigs through the system. So they will end up here, and if I remember correctly, they will send it down. For example, the A flow line. It will be caught here, and then it will be turned around and sent back in the B flow line, so that they do both flow lines. Have the possibility of doing both flow lines, but usually they only do one of them, so that it will come down the A1, stop here, and then it will be sent back the A1, because they want to keep up their production, of course. So every single minute or hour that a field like this isn't producing, and that's quite a lot of hundreds of thousands, maybe even millions of kroners lost in revenue. So if you can shut down just one of the two flow lines in order to do maintenance on it, and then keep the other one operating, and then switch around afterwards, that's a lot better, because then you still have some revenue coming in, instead of shutting down everything and then waiting until you're done doing your maintenance. So that's how they usually operate. And the umbilicals also come in here in the processing system. They are connected in here and down to the templates. And you can see also they are interconnected between the templates. I'm guessing that's sort of a redundancy option that they're using, that they are, in case they have a break inside the connection here, they still have a connection around here. So they use it as redundant options. Here is template A, and as you can see here, there's quite a lot of valves as you get inside the template itself. So each of these, here's the first Christmas tree with its control modules and everything. I think they've dropped showing the control modules on the others, but here you have all 8 Christmas trees shown, and then you have all of the valves inside the manifold part of the template shown here. So everything is being connected, run through. You can see the red ones are the gas production lines, and you can see they are all connected together, but they're separated with valves. So they can, if they want to, they can shut off an entire side of Christmas trees and keep producing on the other side. If for some reason they need to do that for maintenance, they can shut off all of these valves going between them and just send out a flow through one pipeline. So that's one of the possibilities they have. As you can see, there's quite a lot of different types of valves. All of them are ROV operated. It says here that some are hydraulically operated. The ROV ones, the hydraulically operated ones, can usually be manually overridden by an ROV. But there might be some that are completely hidden inside the system where the ROV can't reach it, so it won't be any point in having this override in them. But I think most of them here can be reached by an ROV, so that it has the possibility of overriding them if needed. The reason why they are hydraulically operated, shown like this, is because they are actually operated from ashore. So they sit in their control room and they are operating them there. But if they're down here with an ROV doing work on something else, then the ROV has the possibility of quickly shutting down and opening valves if needed. So here we have, this is the shore part of the flow line going all the way to the shore. And here we have I think it's the D module this one is connected to. Here we have the choke module parts, and we have the Christmas tree up here. So we're basically just looking at the different flows going through here. We get gas coming through the valves in the Christmas tree, going into the choke module, being put into to the correct throttle down to the correct pressure that they want in their system, and then it's released into the flow lines that go to shore. And in between here you have quite a lot of different stuff. You have a flow meter, sand detection for erosion, acoustic sand detectors. They are basically microphones that are listening for the sound of sand that is scraping along the inside of the pipeline. So it's quite a great way of detecting sand inside your pipelines. I've seen some presentations where they could actually use these sort of very sensitive microphones, and they placed them just in the middle of a template, and it was just listening basically to the sounds that were coming from inside the pipelines. They were hitting, the sand was hitting the inside of the pipeline. This was vibrating the pipeline just very slightly. And the vibrations of the pipeline set the water into vibration, and these vibrations in the water reached the microphone. So basically they could hear straight away if there was sand in the system somewhere. They didn't know exactly which pipeline had sand in it, but they would hear straight away if there was a problem in this template. I'm not sure if they have that kind of system here, but I've seen it presented a couple of years ago at a seminar I was attending. And it was really cool that you could actually put it up. It wasn't something that we could hear, so they couldn't like sit in the control room. If you imagine, if you've seen submarine movies where but they're sitting in their sonar room and they're listening to all of these different sounds, and they're, oh, that's that kind of submarine, or that's that kind of whale, and they are listening to everything. This wasn't something like that. You couldn't hear it at all, so it was just picked up by computers. So the computers have been taught what patterns to look for in the sound waves, and then it's just realized that, whoa, here we have something that's not supposed to be here. And then they alerted the operators that they had to check it. So it was quite a cool system.
So in the event that there is sound in the system, how do they tackle it?
They have different ways of dealing with it. Hopefully, if you get too much sand in a system, you would hopefully know about this before you develop the system completely, because then you have to put down some sand traps and stuff. So you have to put down equipment that can sort of get the sand out of the flow before you send it through all of your long pipelines. If this is a problem that is starting to occur as the field is getting older, that you're getting more and more sand in the system, then it's something that you'll have to take into account when you are scheduling maintenance, that your flow lines might not have that much life as you thought they would have, that you have to fix them sooner. Or it might have to be taken into account with the lifetime of the entire field. If you're seeing a steady increase of sand and becoming more and more of a problem for your maintenance, it might have to be valued towards, well, we are getting, as the lifetime of the field is progressing, we're getting less and less gas from it. And we're getting more and more sand. So the maintenance costs are going up while the productivity is going down. So then you have to sort of find a balance point where when we get to this point, then we're going to shut down production, because then it's not making us any money anymore. We're using more money in keeping it going than we are getting from sales. So it's something that's you need to keep an eye on all the time in a system, really. But some fields almost don't have any problems with sand at all, because it depends a bit on the reservoir itself. So it's the structure of the reservoir which is the problem. So if it's a reservoir which is very, very porous and it very easily turns into sand, then it's going to follow the flow. And if it's fairly hard but porous, then it's not going to turn into sand that quickly. So it's I think a geologist would make a better answer than I'm doing right now, but it's very very individual from each reservoir, how much sand you're going to get. So it's something they keep an eye on, and of course they have PhD geologists. They have a whole army of them working, looking at each reservoir, so they know what they're looking at before they start developing something. We also have some valves and flow meters for the MEG line, so the anti-freezing stuff that we are putting into the flow line. So of course we'll need a flow meter, because we want to know that we are actually getting the correct flow out. So if there's been a break in the injection line somewhere along the way, then we're not going to get the correct flow here, because some of our flow is going to be going into the sea instead. And we also need a valve, of course, to get it in the correct dosage into the flow line. Now this is the umbilical. So I see I've forgotten to translate this one, but it says umbilical A and a cross section in Norwegian here. And also everything else there is in English, so it shouldn't be a problem. This is actually just to put a slight pointer back to our CAD stuff. This is a technical drawing. So here you have Hydro and Nexans. You have their title block. So in here you will find all of the most likely the initials of the drawers and the checkers and the approvers and everything in this red part here. You'll find part numbers, drawing numbers with references. You can see they have quite a lot of they have a lot of dashes separating them, and usually like Hydro and Statoil, these large companies, they usually use they have a code for one facility, Then they have a dash, a code for a section of the facility, a dash, a code for what kind of system it's on, a dash, and another code for a subsystem maybe. So they have huge sort of codes that they're following just to try to figure out everything. And if you can remember from last time when we looked at the video that was doing these flyovers of the Nyhamna area where they have the processing plant here, it's pretty large. So when you have this huge area, you have thousands of valves and a couple of many kilometers of pipeline just on that land area. You need to have very good systems of telling you what is where. So then you have these kinds of drawings. Up here is the parts list. So this is a very complicated parts list. You have quite a lot of parts in it. You also have balloons here with the numbers. They are connected to the item numbers in the parts list. So if you find 26 up here, it's showing the casing of the umbilical. You can find it in the parts list if it's possible to read it. It wasn't possible to read it here on the screen. I'm not sure what it is in the printed version. But if it's possible to read it, you can find it in the parts list and read the description of it, see what it's made of and stuff. And here you also have different notes that they've put in with additional information showing a couple of stuff. So even though this is a cross-section of the umbilical they use to deliver all of the power supply and control signals out here, they've still made a technical drawing of it. So they've still created that. So basically everything that is created in a system like this gets a technical drawing. So it's something that you as engineers really have to become familiar with and realize that there are hundreds of ways that these drawings can look like, because every company has its own way of doing it. Because even though we have these ISO standards that we are drawing from in the CAD lessons, most companies always do their own stuff. So they run their own style of technical drawings. And sometimes it can be a bit difficult if you're sitting in a small company like I did in Imenco and you're getting these drawings from Statoil or something. They can be almost a bit painful to work with, because there is so much information that's completely irrelevant to you as this engineer in a smaller company, because the only thing that information is, the only people that information is telling something to are the people that are actually working with that project in Statoil. So they're the only ones that know what it means. But usually you get all of the dimensions and stuff you need in the drawing so that you're safe there. But you often have to have quite close contact with the project engineers in the large oil company, and just sending mails back and forth, trying to clarify stuff. So that is this dimension that I'm seeing here, is this actually the dimension I think it is, or is it something else? So that you have to constantly clarify stuff. Yeah, we'll do a break in just a minute. So what they usually do, if you haven't clarified stuff with the project engineers, maybe you've done it by telephone. You actually call them and talk to them, and you thought you got a very good explanation. But it turns out you misunderstood, so you did something wrong anyway. If you haven't got that one on mail, so you don't have a mail history of it, then that phone call never happened. So if they told you something wrong on the phone because they misunderstood what you were asking, then that phone call never happened. No one is going to admit that they did have a phone call with you. So that it's very good to do everything written down. So do it in your mail so that you have a mail history, because then you can just attach your old mail history if any problems arise. So that's a good tip from me here. We'll do a break then, 15 minutes. Right. The next slide is of the wellhead that they're using in the wells there. Now we've already looked at the structure of a wellhead basically, so I'm not going to go very thoroughly through this. You have some of the diameters shown here, and it's a nice section that they've done to show it. You have an overview of the main components of the wellhead, where they have their outer wellhead, inner wellhead with casings, more casings as we go along downwards. As they are getting deeper and deeper into the well, they need the thinner and thinner diameter of the casings. And then you have the tubing hanger and the production pipe and lower completion with gravel packing. So lower completion with gravel packing in the reservoir zone. I'm not quite familiar what they are talking about here, but if I remember correctly from my own courses that I've done, the gravel packing is that they actually fill up when they've dug the well into the reservoir in order to avoid it sort of collapsing where they've dug it. They fill it with gravel because the oil won't have any problem flowing past the gravel because there will be lots of holes to flow through. So that they fill it up with gravel in order to keep it strong enough that they won't collapse in on itself there. So I think that is if the reservoir is of a fairly sandy type, so that it can sort of collapse and just become a pile of sand there. So that's why they fill it with gravel there, and that's probably also one of the reasons why they have the sand erosion detectors up in the template. So we look a bit more at the surface-controlled subsurface safety valve, or as it's also sometimes called, as we can see here, downhole safety valve. And they have two of them in this case, so they have 1 and 2, which they can close off. So I'm guessing that when they need to close these, they are utilizing the top one primarily, and then if they need to do exchange it because there is some problems with it or anything, they can actually close off the lower one and keep the safety valve closed while they are doing work on the other safety valve. They would still need to have all of the safety measurements in place up top, but it will add a bit of extra safety that they can close the lower safety valve. And they are deeply placed in this case, so they are very deep inside the well. They're not fairly close to the Christmas tree, and that's because of the low temperatures. So they want to avoid hydrates being formed. Because they're not injecting the freeze inhibitors until they're up in the manifold. So down here, if it gets too cold, it's going to freeze a bit. So then they place them further down where it's warmer, so that they're out of the cold zone. Yeah, and here they actually mention that they have the philosophy of using 2 because it creates longer intervals between interventions. And only one of them is active during normal production. Yeah, that was the safety valve. And here's the sequence for when they were installing the entire well. So they ran the 30-inch wellhead first, landed it in the template. Then they do the next wellhead, landed it, and then several hangers and liners in it. Then they run the completion pack, where they make everything ready for the production piping. Then they put the Christmas tree on it, and then they lock it with the H4 connection, which is the clamp part that locks it into place. And then they orient and land the hanger through the Christmas tree. and then 2 crown plugs in the upper hanger they put in here. So here we see the Christmas tree. Yeah, this is the Christmas tree. So we have the tree cap up here, and those are the crown plugs that they mentioned in the last slide. So they have an upper hanger that's placed actually on the top of, in the top of the Christmas tree. So you can see this is a bit of a different design than what we've looked at earlier. In the earlier ones, all of the hangers were down pretty far down in the Christmas tree or just in the wellhead itself. And here we have the production flow coming in, going out to this side. And here's a 3D model of the Christmas tree with its control module and its choke valve module. So remember the clip we saw where they were exchanging a choke module, where the ROV was flying around doing opening and closing valves, and they were having this running tool coming down with an elevator lifting up the choke module. It's more or less the same principle that's being used here. That was on the Kristin field, it wasn't on the Ormen Lange, but it's still more or less the same principle. Might be a bit different design on stuff here, because that's the whole problem with not having standardized solutions for the oil and gas industry. It's that if you have Aker doing the engineering for Ormen Lange and you have Able doing the engineering for Kristin, then they're probably going to look a bit different. The main solution, the principle of everything, is exactly the same, but the small details will be different. So it's I think there would have been huge amounts of money to be saved if in the 70s, when they started doing oil extractions outside the coast of Norway, then if they had just said that we're going to do things like this and everyone is going to do it like that, then I think it would have been much better, at least in the situation we're in now. There we see the Christmas trees. So they're really huge. You can see the guy here on the side. So that's the entire part here. This is just the choke valve, which is placed behind there. And then it's the production module, the control module parts, which is in there, in that sort of tube. So it looks almost like a gas bottle. If you buy a bottle of gas in the store to use on your barbecue or something, it looks almost a bit like that. And that's because, of course, there's only 1 atmosphere inside. So it's a low pressure compared to the outside pressure. And that's because there are electronics and stuff inside it. And in this case, they don't have to replace the entire Christmas tree in order to do maintenance work on choke module or production module, because they have modularized it so that they can do like on the Kristin field. They can exchange only the choke module if needed. If that one is starting to wear down and they need a fresh one, they can send a new one out with a ship. They can connect it, put the running tool down, pick up the old one, and then run the new one down and place it. And then they can start production again. So it will probably take a day or two of work. So this exact Christmas tree won't be producing for that day or two, but still it's a lot better than maybe having to exchange the entire Christmas tree, which probably would have taken a bit longer since it's a lot more weight that has to be done, and you have to possibly have to put down blowout preventers in between and everything. So it's a better solution to do it modularized like this. So for the Christmas tree itself, it has quite a lot of... so this is how it looks like if we strip away all of the yellow stuff here, all of the yellow framework that's keeping everything in place and protecting it. So the orange stuff inside here, that's the Christmas tree itself. And this is how it would look like if we stripped away everything else. So we have the H4 hub up top where we can connect it. Some release rods. I'm guessing those are ROV operated. I'm not quite sure if they are. We have different lines coming into it with connectors, valves. So we have production master valve, production wing valve, annulus master valve, annulus wing valve. So these are the huge valves that are in here. They are hydraulically operated, of course, so that's why they need these large areas, because this is where the hydraulics part is. The valve itself is inside the Christmas tree. You also have the meg line coming in. I'm guessing this check valve is in connection with the meg line to avoid production flow returning into the meg line, because the methylethylene glycol that's being injected, it's supposed to be injected. It's not supposed to receive oil into it, so they have to have a check valve stopping flow in the other direction. And of course, you would have an ROV panel to control all of this, but it's not shown here because it would be in the way. Yeah, another, yeah. I'm not quite sure what the XOV is, so I'm not going to try to explain it. Just in case I'm completely wrong in what I think it is, because I'm not quite sure on it, but I can try to check it up for our next lecture and see if I can figure out what it is. It was because it's not even mentioned here, so I was a bit unsure what the function is. Here's another technical drawing used for the Christmas tree. And we've looked at so much details about Christmas trees now that I think we're just going to run straight past it. Here's another technical drawing, a cross-section of one of the valves. You can see the spring-loaded fail-safe part. And here is the control part for the ROV, so it can come in with a torque tool and it can rotate it to run the valve itself. That's the same valve. This is just the actuator of the valve, and here's the valve part shown there. We've also we did look at the gate valves and stuff earlier on in Appendix A, so I'm not going to go too deep into this. So for the choke module in this case, we have the dosage valve for the meg line that's going in. So it's actually inside the choke valve where it's dosing out how much of this antifreeze it's going to put in. And it has the choke valve itself down here. And then it has a horizontal connection to the manifold. It has a wet gas flow meter just to see how much production is coming out there, which is wise to have, because you will know before the choke valve you have full pressure and you have full flow from the well. But after the choke valve, it's nice to have a flow meter just to tell you exactly what you're getting from the setting you put because you're throttling it down, so you're putting down the pressure, but you could also end up reducing the flow rate. So, and you don't want the flow rate to be reduced, so it's that too much. So you want to know what flow rate you have, and you also have the connection to the Christmas tree itself. Yeah, the components of the choke valve. In this case, it's one of these needle valves, I think it is. Yeah, it's a needle valve, so you have the needle parts in here. So in this case, it's fairly large, so it's more of a nose than a needle. They're calling it a nose, but it's basically just a plug that you have an opening where you have a flow coming through, and the plug can be lowered into the opening and gradually close it. So that's how they're throttling on this one. Yeah, this is just a bit closer up look at the components of the choke valve. Yeah, and they have pressure and temperature sensors both before and after the choke valve, which is nice to have. At least the pressure ones will be nice to have to see the effect of your throttling. But also temperature, because as you know from thermodynamics, temperature, pressure, volume, everything is connected. So if you are changing one of them, you might end up changing the others. So it's nice to know what temperature you're ending up with. And we also know that if we're throttling and reducing pressure, we are creating friction in it. We know this from our hydraulics, which means that you will probably get an increased temperature after the choke valve. So it's nice to keep an eye on what the temperatures and pressures are. And then it's the wet gas flow meter. So it measures both the gas, the condensate, the water rate in the fluid flow. So the water rate is just, as we're down in the high pressure of the reservoir, the water will of course be vaporized along with the gas, so it will be in its gas phase, just like the gases. But then when we get up to the Christmas tree, and especially since we have these low temperatures here, you get condensation of water inside the flow line. And that's why they are injecting these antifreeze stuff, because they don't want clumps of ice and stuff ending up inside the flow line there. And this is the control module, subsea control module, shown just briefly there. I think we go a bit more into it. Yeah, here we have the umbilical coming in into the control module. We have the the Christmas tree here with the well going down. There's the control module. So it's not going directly into the control module, it's going into the Christmas tree, and then it's sent over to the control module. Which is, of course, logical, since they had created this one modular. They don't want the entire umbilical to connect into the control module if they're going to replace the control module. They wanted to have just the connections it needs coming into it. So that's why they have these electrical and optical jumpers, the blue and red ones that are shown here. So if they are going to do maintenance and replace the control module, they can disconnect just the control module, and then they can replace it and then reconnect the new one. The rest there is fairly similar to what we looked at in Appendix A. So now we're done with this attachment and this appendix. I've put two clips in the last slide here, which I'm going to put the slide up along with the lecture. As far as I could see when I was running through this one, which is 1 hour and 80 minutes, it contains the same as this one, but just more. So it has everything that this one has, but it also has even more. But this one was good quality and 47 minutes, and this one was a bit poor quality, both on the picture and on the sound. So it wasn't the best quality of it, but it's covering more. So if some of you want to watch them, they will be available in the presentation that I put up on Fronter. So if you want to have something to look at, if there's nothing else on TV one evening, you can put on one of these and watch them. It's about the Langeled pipeline, the 1,100 plus kilometers that they were putting down. So it's about how they put it down and everything. So it's very, very interesting to watch it. I've seen this one before. For some reason, the one that's on YouTube has hard-coded in some texting in some language I don't know what is. But the audio is in English, so it's no problem keeping track of what you're saying. But it is an interesting one. I haven't seen the full length of this one. I just sort of fast forwarded through it just to see that it contained everything that this one did. So that's an option for those who want extra information. So then we're moving on to Appendix C, which is the Icarus pull-in, or tie-in, or what they call it. So it's a pull-in and connection system. So there's a lot of technical information in here with depth ratings and development of it, fields of application, everything like this. But I'm going to do a brief version of it as we go through these different pictures instead. So this is an ROV operated tool. So we have the ROV up here. So these figures that I put up here, they are in the last section of the appendix, last couple of pages there. So we have the ROV up top here, and this part here is the Icarus tool itself. And here we have a flow line that's been put down. So this part over here will be the template where the Christmas trees are placed and everything. And they're going to connect this flow line to the Christmas tree. So the first thing that happens is that the Icarus is lowered down to the ocean floor. I think we have some better. There we have them. There's just a bit of a shows a bit more dimensions of the both the ROV and the Icarus system. So the first thing that happens is that the Icarus system is lowered down from the ship and just placed in a basket on the seafloor. So the ROV comes over. It picks up the Icarus tool and flies it over to the manifold part. It hooks it up to the manifold. It's basically just a, if we go a bit back here, we can see you have this sort of loop here where you can, it's based almost like a collar, so it just places it on top of the edge that we can see here, and the collar is here, so that it connects to the edge. So it's just a sort of plug and play part. So the first connection here is just plug and play. It's just lowered on top, and then it sits into place, and then it's locked into place with some clamps afterwards, so that it stays there. But the first positioning is very easy with the ROV. And then inside the Icarus there is a winch with a wire. So the ROV pulls out the wire over to the flow line, and it connects the wire to the tip of the flow line. Then it goes back to the Icarus tool, and it connects with the Icarus tool and starts running it. So it starts running the winch on the tool, so the winch starts pulling in the entire pipeline. So even though the pipeline here might be quite a lot of meters away, it is able to pull it in. So it's a pretty powerful winch. I think there are some details about it in the text there. Here they've shown the Icarus tool. They have done a cross section of it so that we can see the pipeline and the connection point. The ROV is still connected to the tool, so it's still operating the tool. And it's it also removes. There is a cap on the end of the pipeline. I think we see it here. So there's a cap there, which is sort of making sure that you're not filling up as you're pulling it along the ocean floor here. You're not sort of dragging it into the sediment and filling up the insides with lots of dirt. So it's a protection cap, and it's removed by the ROV as it's pulling it almost all the way in. And then the Icarus tool sort of grabs onto the pipeline, because until now it's been pulling it with a winch, but now it sort of grabs onto it with these stroke cylinders, and then they sort of pull it into the correct position to get it close enough to the connection point so that the ROV can clamp it in place. And then when it's clamped into place with the connector, the ROV can just lift the Icarus tool off and place it back in its basket, and then they can both be pulled up to the surface. Here are just some detailed shots of the clamps, I think it is. Yeah, it's the clamp. And here's a good visualization of how they did it when they were putting it into place. I can't remember quite which field this was. Let's see if it says so in the text. No, it didn't say so in the text. I don't think you have this one in your appendix either. This is basically, I've just scanned, because Jens Christian, who usually does this course in Norwegian, he uses a lot of these overheads, the transparent overheads. So I've scanned one of his very, very old overheads. So I don't have all the text here, so I can't remember quite which field this was. But I'll explain to you what's happening here. So we have this connection area where we are going to connect the flow lines. So we want the flow lines that are going for the production, they're going to be connected into this side. And then we have these that have been curved here. They are connected to the field itself. So for these, they use the Icarus. They can use the Icarus and just connect to the edge of the pipeline, which is the continuous line, and then they can pull it in. And as they pull it in to connect it, it's going to be straightened out into this dotted line. So the same is going to happen with this other one, which is the continuous line here. So as they pull that one in, it's also going to be placed approximately where the dotted line is. So those are most likely flexible pipelines. So these layered tubes stuff. And because they have these very huge curves right here. But on the other side here, they're going to connect this oil export pipeline, which is a layer route here, and then there's a gas export pipeline here. And what they're going to do is, step by step, they're going to pick up the end of the oil pipeline, and then they're going to basically drag it up here so that they get this curve on it. They're going to continue dragging it up here so they get this curve, and continue dragging it up here, get this curve onto it, and then all the way up to where it's in the D position. But this is done by a ship. So this is a vessel that's pulling it into place. But then when they've placed it up here, they can use something like the Icarus tool, and then they can connect it, pull it into the correct position. And as you can see here, the curve here is quite a lot. This was a straight line, and they've pulled all of this curvature in it. And this is a steel pipe. This isn't a flexible one. But as I explained a bit in the break, is that if you have a 12-meter pipe that's 30, maybe 40 inches in diameter, it's a pretty huge pipe. And if you put a chain around the middle of it and you lift it, you can actually see that it's sagging a bit. And that's within the elastic zone of the material. You could put it under pressure and push it even more into a curve without it being deformed, so that when you release the pressure, it would snap back. And if you lowered it down to the ground again, it will be completely straight. And if you put quite a lot of these 12-meter sections in a row, then the added curvature that you get from each of these 12-meter sections ends up being something like this, so that you can get the large curves that you get. And that's also what you need when you are putting the pipelines down on the seafloor, is that you need to know basically what is the smallest radius that I can have on my curve, which is basically the sharpest curve that I can have. And then you have to choose your route to avoid anything that's even sharper than that. So it's quite amazing actually how they can manipulate the steel in this way. But as I also mentioned in the break when we were talking about it, it was that when you've already put all of the strain on the pipe, you're already flexing it a lot within the elastic zone. If you then have something unexpected happen, if there is a landslide that hits the pipeline and starts moving it, if there is a fishing vessel that drops an anchor and snags the pipeline and starts dragging it, then you will very quickly move from this elastic bending and into the plastic one, where you're deforming the pipeline, where it's not going to bend back again. And that's when we have to go in and do replacements of sections in the pipeline. And that's a pretty huge job to do. So there is a place here in Haugesund, Chillingøy, all the way to the north of the town, where they actually have a pipeline repair system, which is it's a standby venture, which is I think it's paid for mostly by Statoil, but also by the other oil companies here. So Statoil has the highest share in it, but the other oil companies are also contributing to paying for this. And I think it is Technip that is running it right now. So they have a couple of years of a contract, and then another company gets the chance to bid for the contract. So it changes every now and then which company it is that runs it. But this pipeline repair system, they are basically in standby. So they are sitting out there in Chillingøy, in their base there. They have all the equipment they need to start fixing pipelines. And as soon as something happens somewhere on the Norwegian continental shelf, that there is some damage to a pipeline or anything, then they will start mobilizing. So they will get the first available vessel that they can get their hands on. They will get that one into their Chillingøy base. They will start loading up their equipment, and then they will move out. And I think they have a response requirement of 16 days or something like that. I can't quite remember. It's been a while since I was visiting them and getting a tour there. But they have sort of a requirement from their owners that within this many days you have to be able to respond. So if you're not exactly in there, because if it's all the way up in the Barents Sea in the north, then they can't manage to do that. But they have to at least have gotten away from here, so they have to be on the way to the location where they have to do the repair. So they are working hard to stay ready at all times. And if something should happen here, that you get a break in the line, basically what they do is the same as what we saw when they were connecting these two pipelines in the animation last lecture, where they had placed one pipeline in the Baltic Sea, one from one direction and one from the other direction, and then when they met in the middle, they were going to weld them together. And they had this welding habitat, which they put down with a robotic welder and stuff, where they created an atmosphere inside so that they can weld instead of welding inside with water in there, because that creates very poor welds. And it's basically the same that they would do to fix parts of a pipeline. So they would bring some lengths of pipeline with them. They would survey the area, figure out how much of the pipeline do we have to exchange, and then they would go down and they would cut off the pipeline and put a new part of the pipeline down and weld it in place. So that's their work, basically. And here you see the rig part that's up here. template stuff. This is the same one, so you see you have you can connect the pipeline in here from the oil field and there, and then you have the flow lines going out here. And this is sort of to show how they are how they move the pipeline. Over here, the yellow dot there is this structure. So they have the ship that puts down balloons, actually, just like we saw on the clip. Also, they also used balloons to make the pipeline lighter, and they do calculations beforehand because they know how much gas they're going to fill into each balloon, so that they know how buoyant it's going to become, and then they can calculate the length between each balloon. So they put the balloons on, and the ship starts pulling it, and it pulls it until it's close by the connection structure. And then they can come down with ROV and connection tools. So then they get to connect it into there. And here you can see that's the oil export line, which we saw. And here's the gas export line. So the pre-deflected one was the straight line here before they started pulling it upwards. So the oil export actually seems to have the sharpest curve. So even though the gas export was further away, they managed to get a nicer curve to it. Yeah, that was the last one. Then we're done for today. I think we'll do Appendix D and E next week. No, next week, but on Thursday. Yeah.